In this video, we'll briefly go through what is turning effect of forces. Turning effect of forces is basically moment, and maybe let's introduce you to the formula. The formula for moment is m equals to force times distance. Alright, so because the SI unit for force is Newton, the perpendicular distance is a distance, so it's meters. So it's very easy. Moment is Newton meters. Alright, and the definition of moment is actually very simple if you know the formula. Since it's force times distance multiplied by distance, and if it's multiplied, the times here, it is a product of the force F and the perpendicular distance, not just any distance. It has to be the perpendicular distance, but where is it from? The distance is from where to where? It's from the line of action of the force to the pivot. So what does it mean? Let's take a look at the example over here. You have a force which is 10 Newton and it's applied upwards on the end of the rod here, and this end here is the pivot. It's like a hinge here. So this rod can either turn anti-clockwise or clockwise, depends on the direction of the force. So for this case, the force is upwards. You should know that it will go around the pivot in this anti-clockwise moment. So what is the anti-clockwise moment? Force times distance. As you can see here, the force is 10 and the distance. This is already perpendicular distance. This is the force. This is called the line of action of the force. Basically, you just extend the line where the force is. Okay, just extend it. And it has to be perpendicular all the way to the pivot. So this is the perpendicular distance that I want. So it's 2 meters and the moment will be 20 Newton meters. Alright, now let's take a look at another example. If you have this force but it's still 10 Newton, but now it's acting downwards, you should know that it will create a clockwise moment about the pivot. And what is the moment? The clockwise moment, force times distance, and the force is still the same, and the distance is actually 1, so it's 10 Newton meters and it's clockwise. So basically the moment, how big the moment is, depends on the force that you apply, and also the perpendicular distance from the pivot point. So there are only two types of moment. Either is clockwise moment, you can follow your analog clock, it will be going in this way that you're familiar with, clockwise moment, or anti-clockwise moment, so it's going this way. So but for a system, if the sum of clockwise moment and the anti-clockwise moment, they are equal, we say that the body is in equilibrium or balance. And when that happens, you can say that principle of moment. So this definition is very important and consists of 3 parts here. When a body is equilibrium, is balanced, okay, the sum of clockwise moment is equals to the sum of anti-clockwise moment. By the way, take note, it's not force. There's no such thing as clockwise forces or anti-clockwise forces. It's moment. And they must be calculated or with respect to the same pivot. So these 3 points must be inside your definition. Now let's take a look at the example where if the diagram on the left here, if I were to tell you that this is balanced, it means that this system obeys the principle of moment where the sum of anti-clockwise equals to the sum of clockwise moment because it's balanced. So if you can take a look at here, so this x here, this force, the weight Wx is creating a clockwise moment, where the W is creating a clockwise moment, Y will be a clockwise moment about this pivot. Now this is suspended by a string, so you can treat it as this is the pivot point. So the rod will actually just rotate about this point here. So what you need to do is basically anti-clockwise is x times the distance x, where is from the line of action of the force x all the way to the pivot, let it be dx. So you have to find this distance, and that's the only force that creates anti-clockwise. Let's go to W. W is clockwise times the perpendicular distance from the line of force to the pivot. So this will be the dW that I should be looking for, and plus, because that's why it's called the sum. So now this is another force y, so it's y times the perpendicular distance of dy, and the distance from the line of force all the way to the pivot, this is your dy that you should be looking for. So you can form this based on principle of moment, and you can find any unknown that's given to you. One last important concept is, if you look at this system here, it's balanced, it's in equilibrium. In other words, it's like it's suspended in the air because of this string holding onto it, or the support. This pivot is supporting the whole rod. Now there's two conditions when something is in equilibrium, and almost all students will know that when it is in equilibrium, the principle of moment will be applied here. This condition is met where the anti-clockwise equals to the clockwise moment. But you must also remember, you have learned your Newton's first law. This object is actually at rest. Okay, so that means to say the sum of the upward force. In this question, all the forces are either upwards or downwards. So the total upward force must be equal to the total downward force. The net force acting on the rod will be equals to 0 Newton. If you understand this concept, so you can actually form another equation. What if I need you to find the value of T? So you have to understand, applying Newton's first law, net force equals to 0. So my upward force, which is T, alright, is equals to the total downward force, which is your X, the weight of X, plus W, let's say that is the weight of the rod, and plus the weight of Y. So that is another equation, and you can find the tension or the force acted by the pivot on the rod upwards. Okay, or in other words, if I were to simplify or draw the free body diagram for the rod here, so you have the rod here, there's upward force T, there's downward force X, there's the weight of the rod X, W, and finally the force Y. So you can see that there are 4 forces acting on the rod. So the upward force is equals to the total downward force. That's how you can solve for the value of the tension in the string. Now let's pause for a while. Some of you might be wondering, this force, just like X, W, and Y, they are forces acting on the rod over here, but why is this T, the force T, the tension T here, or the force acting by the pivot, is not reflected in the principle of moment where you apply your anti-clockwise equals to clockwise? Okay, so you have to take note that because this T, yes, is really there, but the thing is, the line of action of the force T passes through the pivot point. If it passes through the pivot point, there's no perpendicular distance. This distance here will be 0. That's why T, it is present there, is acting on the rod, but it will not create any moment about the pivot. So that's the reason why it's not reflected on the left hand side or the right hand side. So this part you have to understand, and that's the explanation for that. So these are the basic concept for turning effect of forces. Now let's dive into some examples where we will show you the typical basic questions where it's a horizontal rod and all the forces are perpendicular to it. In this first question, you're given a uniform rod that's pivoted at the midpoint. There are 3 forces, which is 5 Newton, 4 Newton, and 2 Newton acting on the rod. And the question asks you, is the rod balanced? So you cannot assume it's balanced, therefore you cannot apply your principle of moment where you cannot assume that the clockwise equals to anti-clockwise. Some students show it this way, and then after that the answer here and here is not the same, then they conclude. But that's the wrong presentation. So what you do is you should do it separately. So you find your anti-clockwise moment and the sum of clockwise moments separately, and to see what is the value and are they the same or not. Now let's take a look at the 5 Newton, and I hope you understand that this 5 Newton is going to create a anti-clockwise moment about the pivot point here. This is like the center of the circle. This 5 Newton will cause the rod to rotate in this way, anti-clockwise. So let's draw it here, anti-clockwise. This 2 Newton force is on the right hand side, is downwards, is going to create a clockwise moment about the pivot. So this is clockwise. These two are more obvious, but for the 4 Newton here, now you have to understand that the force on the left hand side of the pivot does not always create anti-clockwise moment. It depends on what is the direction of the force. So in this case, this 4 Newton is upwards, and it's going to pull the rod up and rotate it in the clockwise direction. So this 4 Newton is going to create your clockwise moment, just like the 2 Newton. So if you understand that, let's go about to solve this. So for the anti-clockwise moment, and you know moment is force times distance, so the 5 Newton is the one that creates anti-clockwise, and the perpendicular distance is from the line of action of the force all the way to the pivot. So this distance, which is just 2, and the total anti-clockwise moment will be 10 Newton meters. So that's it for anti-clockwise. Let's go to the clockwise moment. Let's start with the 2 Newton force times the perpendicular distance, which is from the line of action of the force all the way to the pivot. Take note of that, and it's here clearly indicated already. It's just 2 meters, and because it's called the sum of clockwise, this 4 Newton is also creating clockwise, so I do it separately and then sum it up. So it's 4 times the perpendicular distance from the line of action of the force all the way to the pivot. So this is 1.2, and this, if you sum them up, that will be 8.8 Newton meters. So because they are not the same, so you can conclude it is not balanced. And if I were to ask you what is the net moment, so it's a bit similar to your net force or resultant force. So you just take the bigger anti-clockwise moment minus the smaller clockwise moment, and you have a resultant or net moment of 1.2 anti-clockwise. So if you let go of this system will actually rotate anti-clockwise, and the moment will be 1.2 Newton meters. So in this question, you are given a uniform plank. It's pivoted at the midpoint, so it's at the center of gravity as at the center here, and there are 3 boxes acting on the plank, and they are all downwards. That means to say this 20 Newton is downwards, 5 Newtons is downwards, likewise for the unknown weight of the box that you're going to find later on. So firstly, in a way they are trying to guide you. They ask you to find the moment due to the 20 Newton box, which is the one over here, and you should know that the pivot is here. This 20 Newton is going to create a anti-clockwise moment about the pivot point. So A is very straightforward, and they are helping you. So you know that 20 Newton is creating a anti-clockwise moment, and moment is force times distance. So in this case, 20 times from the line of action of the 20 Newton force all the way to the pivot. And this plank is given to you is basically 1 meters, 100 cm, and all these are the markings on the rulers. Okay, so you can treat this as a meter rule. So you have to be very careful. This is the 5 cm marking, the midpoint is 50 cm, so the distance from here to here is actually 45 cm. So this is, so the distance here, if I had to write it here for you, 50 minus 5, the perpendicular distance is 45, and if you solve it, that will be 900 Newton cm. So in this case, because the length is in cm, it's okay to leave it in cm. So make sure everything is consistent. That's more important. So for part B, they asked me to find the unknown weight of the box to make this thing balance. Because it's balanced, then for part B, I'll be applying my principle of moment, where the anti-clockwise moment is equals to the clockwise moment. So like I say, this question is guiding you. Part A, you are basically finding this left hand side anti-clockwise moment, so there's no need for you to redo. You just put here 900. Now for clockwise, this 5 Newton box here is creating a clockwise moment, likewise for this W. So let's do it separately. 5 times the perpendicular distance is from the line of action of the 5 Newton all the way to the pivot, so it's 65 minus 50, so the distance is only 15. And because it's sum, okay, I'll just write below. So now let's deal with W times the perpendicular distance. This is at the 85 cm mark, so from the line of action of the force all the way to the pivot. So the distance that I should be looking at is 85 minus 50, so that will be 35 cm. So if you can solve it, okay, So this 900 is equals to 75 plus 35 W, and then you can solve for your W, which is 23.57, and let's round off to 2 sig fig, 24 Newton. So if this W will be 24 Newton in order to balance the whole rod, the meter rule. In this third question, you are given a uniform meter rule of 100 cm. It has a mass of 5 kg pivoted at the 30 cm marking on the ruler, and it's given that this system is equilibrium, is balanced. For part A, you're required to find the weight of the rule, and I hope you can remember W equals to mg. The mass of the ruler is already given and it is in kg, that's good, times gravitational field strength on Earth is 10, so that would be 50 Newton. And you're supposed to indicate the weight. Now this word here, uniform, is very important. That means all parts are, the density is the same, every part is the same, so the CG, the center of gravity, will be exactly at the center, so this will be at the 50 cm mark, and you draw the weight vertically down from the center of gravity. Do not draw your weight this way, you will be marked wrong. Okay, so it's acting down from the CG, and you just put here, that's the weight of the meter rule, and that is 50 Newton. So next one, finding the magnitude of the force F over here, left hand side of the pivot, that balance this whole ruler. Now, because it's balanced, I definitely can use principle of moment, or another way of thinking is whenever they ask you to find an unknown, I have to apply principle of moment. So applying principle of moment, the anti-clockwise moment is equals to the sum of the clockwise moment. So for anti-clockwise moment, I hope now you are able to identify F is creating an anti-clockwise moment about the pivot point, and your W is creating a clockwise moment. Likewise for your 10 Newton is creating a clockwise moment. So let's continue. So anti-clockwise force time from F, the line of action of the F is over here, and the perpendicular distance is all the way to the pivot, so that will be 30 minus 5. Okay, that will be the perpendicular distance that you should be looking at. And the next one here, clockwise, which is your weight of the ruler, 50 times. For the perpendicular distance is from the line of action of the force all the way to the pivot, so it's 50 minus 30, and plus, because it's there's another 10 Newton here that's creating clockwise moment, 10 times the perpendicular distance from the line of action of the force all the way to the pivot. So it's all the way from here to here, so it's 80 minus 30 because the pivot is at the 30 cm marking. So the rest is math. Okay, so it's 25F is equals to 1000 plus 500, and just solve for the unknown F, that will be 60 Newton. So you need a 60 Newton force here to balance the whole ruler. Now let's extend the question a little bit. If I were to ask you to find the force that is acting on the ruler by the support. Now the support is this pivot here. You're placing the ruler on it. That means to say this force acting by the pivot on the rod is upwards. Let it be FP. Okay, if I ask you to find the FP here, you're going to apply, because this system is equilibrium, it's like this rod is at rest, so you should think about your net force acting on the rod has to be 0. So you have to draw for you the free body diagram again, just to show you this force acting on the rod is pulling it down, this W is pulling it down, this 10 Newton force is pulling it down, and the only force that support in order to be net force 0 is actually this FP. So you should know that FP, total upward force, equals to the total downward force. So therefore you can now find the FP, because you found F already 60 plus the weight 50 plus 10 here, so total will be 120 Newton. That's how you find the force acting on the ruler by the pivot. So if the question asks you this, I hope you can solve this. And of course, another common question, they will ask you, why is this FP not involved not reflected in this principle of moment equation here. And as mentioned earlier on in the video, because this line of action of the FP passes through the pivot point, there's no perpendicular distance. Moment equals to force times distance. This line of action passes through the pivot point. This perpendicular distance is 0, so no moment created by the FP. In this last question, you're given a uniform rod of 4 meters and it has a mass of 2 kg and is held stationary as shown above. That means to say this thing is balanced. And the first part, they ask you to indicate the weight of the rod on the diagram. And as you know, the word here, uniform, is very important. So all parts are the same. So the center of gravity will be exactly at the midpoint. And to draw the weight, you have to draw it from the center of gravity vertically downwards. So W equals to mg. The weight is already in kg, that's good, times 10 Newton per kg. That's the gravitational field strength. And you know that this is 20 Newton. That's the weight of the rod. And so the distance from the CG all the way to the pivot, because it's half of it, so this will be 2 meters. These are things that you must pick up. And for part B, they ask you to find that unknown force, the minimum F that's required to balance the rod. And I will have to use my principle of moment. So applying principle of moment, so the sum of anti-clockwise moment equals to the sum of clockwise moment. Now let's analyze the 3 forces here, 5 Newton, 20 and 10, and plus the unknown F. This 5 is clockwise, this 20 is also clockwise, this 10 is clockwise. The only anti-clockwise moment will be the F here. So if you know that, so the anti-clockwise, there will be the force times the perpendicular distance from the line of action of the force, which is here, all the way perpendicular distance to the pivot. So it's the whole length of the rod. So it's just 4 meters. And for clockwise, let's do it one by one. So let's start with the 5 Newton times the perpendicular distance. And it's from here, this is the line of action of the 5 Newton, perpendicular distance from to the pivot. So the distance will be 1.2. So it's plus because it's a sum. You have to sum all individual moment together. So the next one will be the 20 Newton of the weight of the ruler, the rod here. So this 20 Newton, the line of action is here. The perpendicular distance is from the line of action of the 20 Newton to the pivot. So this will be 2 meters times 2. And the last one, I just write at the bottom here, the 10 Newton force. Now take note, the 10 Newton force, the line of action is over here, and the perpendicular distance that I want is from the line of action of the force all the way to the pivot. So this is the distance that I want, and it's not given to you, so you have to work it out. But what you know is the distance here to the right hand side of the rod is 0.8 given to you. So to find this distance, that will be 4 meters minus 0.8. So let's put it in here. So it's 4 minus 0.8 over here. So if you work it out, so 4F is equals to 6 plus 40 plus 32. And this 4F will be 78, and therefore you have F equals to 19.5 Newton in order to balance the rod. Now let's extend the question C. Indicate the force FP acting on the rod by the support. This is the support, is like at the pivot here, and the rod is resting on it. So some students may be confused. Do I draw the force upwards or downwards? So the answer for this is because this support here is actually pushing the rod upwards to support it. So this FP is actually upwards. But what if you were to think that this is, can it be downward? If you think that it's downward, okay, that would be wrong because all these are anti-clockwise moments. So this whole rod will not be in equilibrium. It will rotate. So it will never be downwards. So lastly, if I have to ask you to find the value, the magnitude of the FP that's acting on the rod by the pivot, so how are you going to do it? You're going to apply your net force equals to 0, Newton's first law. Let me sketch out the free body diagram for the whole rod, which will help you to visualize this is the unknown F that you found in part B, and the answer is 19.5 Newton. And this is the weight, 20 Newton, pulling down the rod. Likewise for this 10 Newton, this 5 Newton. And that's why this FP has to be upwards. So this may be clearer to you. And applying net force equals to 0. So the total upward force is FP plus 19.5. That must be equals to the 5, the sum of total downward force, plus 20 plus 10. And from here, you can actually solve for your FP in newtons. So that's how you do the question. So I hope this video will help you to understand the basic concept of turning effect of forces, moment, and how you go about applying the basic concepts to solve these basic questions. Okay, thank you.